Okay, let's look at another example of the application of the coefficient of the energy equation. Remember, we had like the coefficient of energy equations here. We're just going to apply if the distribution of the velocity is like this, and if it's not like the uniform, for example, we introduce another like a coefficient called alpha, applies to the velocity head, alpha v squared over 2g. So it depends on the like the situations. If it's like the different types of the flow rate, for example, regime, like it's normal, laminar, or turbulent, we just have like the different types of the like the this coefficient for alpha. And we had the same for beta for applying to the momentum equation. So both variation of both coefficients varies between like 1 to 2, specifically alpha. Beta is just going to just change less variable, like it changes between 1 and 1.33, the maximum 1, if it's like a flooded river valley. But I mean, for the alpha, it just depends on the situation. Even for the laminar flow, it can be up to 2, but for the flooded river valley, so it's just going to be like between 1.5 to 2. So with that example or introduction, let's go with some examples of the flow discharging throughout a gate. We have like a vertical lift gate like this one, and we're just going to see how the system works. Okay, for this example, what we have is that the depth of the water behind the gate is given to us. It's like a 3.4 meters, and there is some velocity, but we assume and we know that the velocity is not too much high. But after the gate, once the water release behind from the like the lower part of the gate, the height or the depth of the water drop to 1.2 meters. And we know that the kinetic energy is high, so the terms of the velocity head, like the alpha 2 v2 squared over 2g, is much higher. So we have some assumptions here. So the water depth from upstream of 3.4 meters drop to like the 1.2 meters in at the downstream. And the velocity distribution upstream is like a more or less uniform, but the alpha one is like a 1.1. However, because of the significant variations in the downstream, it's just going to be like a much higher and becomes like a 1.55. The channel has got a like 4 meters wide, so we're just going to need to, and we have like the horizontal bed, so it's completely horizontal in this section. For example, before and after, there is some sort of like probably might have some sort of like the gradient, but for this example, it could be completely horizontal. But it's absolutely fine for like a very short like a period. It becomes like the or short like a distance becomes like a completely horizontal. Assuming that we have no energy head loss, okay, so the question here is to calculate the discharge. So let's see how we can calculate the discharge here. First of all, you're just going to write the continuity equation. We have like the continuity equation A1 V1 is equal to A2 V2. So we have the A1 and A2, and we need to just calculate the relationship between A1 and V1 and V2. So the A1 is like a 3.4 depth times 4 meters width. So A1 times V1 is equal to A2. A2 is like a 1.2 meters high and 4 meters wide. So we're just going to write that one as well as times V2. So the relationship between V1 and V2 is equal to V1 is equal to 0.353 V2. Okay. So with that assumption, let's go and write the Bernoullt equation. So we're just going to write the Bernoullt equation because we know like the P over rho G and Z. Z is the same because we have like a completely horizontal. So we can just remove the Z and we can just use only the P1 over rho G, which is like the depth of the water. So we're just going to write that one depth. The P over the rho G is like the depth of the water. Like we can write here the P over rho G is like a 3.4. The velocity head term, okay, alpha 1 V1 squared over 2G. And on the right hand side, P2 over rho G is like a 1.2 meters height, or the pressure head of the water, like a 1.2 plus velocity head of second the section, alpha 2 V2 squared over 2G. Substituting the values from the above like relation between V1 and V2, we can write like a 3.1 times 1.1. Alpha 1 is like 1.1 times V1, we can just like write the equivalent value for the V2, 0.353 V2 squared raised to the power 2 over 2g. On the right hand side, 1.2 plus 1.55, alpha is 1.55 times V2 squared over 2g. So we're just gonna simplify this, the second term on the left hand side. So it's just gonna be like the 0.0070 V2 squared plus on the right hand side 1.2 0.0790 V2 squared. Okay, so that's it. So the V2 can be calculated here 5.53 meters per second, and the Q is here is easily calculated 1.2 times 4 times 5.53. You know, the A2 is like 1.2 times 4, so it's like this one. Height times width and times velocity that we calculated here. So the result is like a 26.54 cubic meters per second. Just bear in mind, like the velocity 2 is like a relatively high. You know, we don't normally have like a we can say like this is like a high velocity. This is definitely the velocity after or higher than the 3 meters per second. So it is like the high. In other words, you can calculate the V1 and you can write the continuous equation and calculate the flow discharge by using the equation of the, for example, Q is equal to A1 V1. So this is an example of the energy equation.